Okay, so students, today's lecture, that is the second lecture for the real numbers, would cover the following topics. I hope you have taken the assignment that we provided you with the concept lecture 1, and we will be discussing the same in the doubt class. So I will encourage you guys to practice all the questions, and whatever doubts you have, you just post it in the doubt section, and we can take those up when we are interacting live on the next doubt class. So to start with, we will first be starting with the problems related to HCF and LCM, which was the topic that we were covering in the last class. So it will just be a kind of a recap and a few word problems, and also the linear combination. HCF, expressing HCF as linear combination of two numbers, is a very difficult um, concept, and we will be trying to cover that up so that you are able to solve questions related to that. Other than that, we'll be working on the irrationality of numbers and the decimal expansion. So let's get going. What does this first question say? It says that there is an army contingent of 616 members that has to march behind an army band of 32 members. So there are two groups. One is the army contingent of 616 members, and the second is an army band of 32 members. And the two groups are to march in the same number of columns. So you have 616 members in the contingent who will be walking in columns. So this is how they would be marching. There will be several rows, and this is how it will be. So this will be the rows. Here I have shown 4, but let these be n. We don't know the number, exact number. So you can just put a dot here so that we are not sure of how many rows and columns are there. But again, the total number of people here would be 660. This is the army contingent, and behind this you have the band, and the band has to walk in the same number of columns. Columns would be this way. So they have to walk in the same number of columns as the army contingent, but obviously their number of rows will be less since they just have 32 members. So this is what the thing is going to look like. There will be n number of rows, n1 number of rows, or a rows over here and b rows over here, but the number of columns is going to remain the same, and let that number of column be n. So there will be 616 in this chunk and 32 members parading in this chunk. Now we have to find the maximum number of columns in which they can march. So we have to find the maximum value of n that is possible here. Okay. So let the number of rows here in which the army contingent walks be A. This would be the number of rows. And the number of rows in which the army band walks be B. So we know that the number of people in this particular grid is going to be 616. And what is it going to be? It will be n into A. N into A is going to be equal to 616. For example, let's just take a grid like this. So you have two columns in this grid and you have three rows. How many people are there in this grid? It's equal to 1, 2, 3, 4, 5, 6, which is equal to number of rows into number of columns. So this is what we have done here. The number of people in this grid would be number of rows into number of columns, and it is given that it is equal to 660. So this will be the equation 1 that we have. What is the second equation? Second is n into b. For the army band, it is going to be n into b, and this is going to be equal to 32, which is given. We have to find n, and n has to be the largest or the maximum value. So again, when you look at these two equations, you see that n is a factor of both 616 and 32, and n has to be the maximum that it can take, and hence n will be the HCF of 616 and 32. This is what it is going to be. How do you take out the HCF? You have already learned you can use any of the methods that you know of, and one would be the prime factorization. So I would take prime factorization here, and it will be 308 over here to 154. It will be 77, 7 here, 11. Right? This is what the prime factorization for 616 is going to be. So it's going to be 2 cube into 7 into 11. 32 can be factorized as 260 to 8. We have 4 here. We have 2 to the power 4. And what was HCF? HCF is the lowest power of the common prime. The common prime is 2, and the lowest power of 2 here is 2 cube. So it's going to be 2 cube, which is equal to 8. The HCF is going to be 8, and hence the value of n is going to be 8. Thus we can say that the maximum number of columns in which 616 members of the army contingent and 32 members of the army parade can walk, such that they walk in same number of columns, is 8. And I hope you understood how and why we applied the HCF here. You might be tempted to say that whenever you have to find the maximum number, you would always find the HCF. But this is not the case always. And you'll be having a few questions in your assignment, and we'll be covering an illustration as well that will showcase that particular thing, wherein it might not be maximum here, but you still have to calculate the HCF, or it might not be minimum here and you have to calculate the LCM. Let's see the next question to understand it better. Okay, so now in this question you have a rectangular room whose dimensions are given. So you have a rectangular room in which one dimension is given as 1872 centimeters. 18 meters and 72 centimeters is 1872, and you have 1320 along this direction. And you have the whole room that's paved with square tiles. So you have, figure might not look exact, but it's good enough for understanding, I guess. So you have the floor actually, which is paved with square tiles. Let the size of this be A. So you have A and along this line and A along this line. Now it said that the entire floor is covered with square tiles. We have to find the minimum number of such tiles. Now, for somebody who took maximum as the keyword for finding HCF would say that here maximum is not written, so we don't have to find HCF. And since LCM is least common multiple, and here we have the word minimum written, so we need to find out the LCM of these two numbers, would be wrong. You don't have to always go with the word maximum or minimum. You should always work on the fundamentals and try to create the equations and then see for yourself whether it classifies for an LCM problem or a HCF problem. So we will not make a judgment as of now. We will first form the equations like we did in the last question. So let the size of each tile be A. So size of each square tile is equal to A centimeter by A centimeter. Okay. Now, along this length, there will be m number of tiles. M tiles would be kept here, right? 1, 2, 3, 4. We don't know how many tiles are kept, so let's call it m. And similarly, along this height, n number of tiles would be placed. So 1, 2, 3, 4, 5, 6, and n. Now, along this is A. How many times do we have A here? We go on adding A m times, that is A into m. Along this is A. This is 2A, this is 3A, 4A, and how long till we go up to? We go up to m times because there are m tiles. If there were 5 tiles, the size would be, the length along this would be 5A. If there were 10 tiles, it will be 10A. There are m tiles, so it will be m into a. And what is the whole length? It's given as 1872. So one equation that we get here is a into m is equal to 1872. This is the first equation. What about this direction? You have a how many times? N times. So you have a into n, and this will be equal to 1320. So you have the second equation. Alright. Now, what does it say? It says we have to find the minimum number of tiles. What is the number of tiles? We don't have to find A because A is the size of each tile. Do we have to find the size of each tile? No. We have to find the minimum number of such tiles. What is the number of tiles? The number of tiles is how much? For example, you have a grid. Again, I'll show you with a grid. Let's make it a rectangular grid because we have a rectangle here. So here, how many squares are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. How many squares along this line? 4. How many along this line? 3. So how many total squares you have? 4 into 3. Similarly, in this particular rectangle, how many squares you have? M. How many squares you have along this line? N. So the total number of tiles, what we have to find is the total number of tiles. So the total number of tiles here is m into n. And what do we have to find? The minimum number of such tiles. So we have to find the minimum value of m into n. The number of tiles will be minimum when m into n is minimum because that is what the total number of tiles is. So we have to find the minimum value of m into n. What will be the minimum value of m into n? The value of m into n will be minimum when both m and n are at their least values, that is they are minimum. So when you are calculating this, m into n has to be minimum would mean that both m and n take their least possible values. And what will be those least possible values? You go to equation 1. And what do you have in equation 1? In equation 1 you have am is equal to 1872, which would mean that m is 1872 by a. And from this equation you have n equal to 1320 by a. Now we have to find the minimum value of m. As we go on increasing the value of a, the value of m is going to go on decreasing, which can be seen from a simple example. You have 1 by 2, 1 by 4, 1 by 8. There are 3 numbers, okay? Which is the least of them? 1 by 8 is the least of them. Why? Because when the numerator is same, you go on increasing the denominator, the number is going to go on decreasing. So for any number, larger the denominator, smaller the number will be. So for m is equal to 1872 by a, if we keep on increasing a, the value of m will keep on decreasing up till the time when a takes its maximum value. So at the maximum value of a, the value of m will be minimum. Why? Because as we go on increasing a, m decreases. So when a is at its highest value, m will be at its minimum value. So to calculate the minimum value of m, we have to calculate the maximum value of a. Similar is the case with n. To calculate the minimum value of n, you have to calculate the maximum value of a. So the first thing that we now need to do is calculate the maximum value of a. How do we do that? We look at these two equations. We see that a is a common factor of both these numbers, and we have found out that we need to calculate the highest value of a such that we get the least value of m into n. Least value of m and n will give you the least value of m into n. So common factor and largest value. So a will be the HCF of 1872 and 1320. How do you calculate the HCF of 1872 and 1320? you use the Euclid's division algorithm. So you have 1872 is equal to 1320 into 1 plus how much is left? 552 is left. The remainder is non-zero, so you go to the next step. So you have 1320 is equal to 552 into 2. 552 into 2 will be 1104. So you have 1104. So 216 will be left out. You have 552 equal to 216 into 2. That's 432. So you have 120 left. So you have 120 here. Again, the remainder is non-zero. So you go to the next step. So you have 216 is equal to 120 into 1 plus how much is it? 96. So you have 96 as the remainder. In the next step, so you have 120 is equal to 96 into 1 plus 24. Next step is 96 is equal to 24 into 4 plus 0. We get a 0. So the HCF is 24. So A is equal to 24. That means the size of each tile is going to be 24 centimeter. But is this what is required? No, we have to find the minimum number of such tiles, and the minimum number is m into n, which means we need m and n both. So m can be obtained from here, and m will be how much? It will be 1872 divided by 24. How much do we get? We cancel it out. So you have 3, 1, 2, you have 78, right? And n's value will be 1320 divided by 24. And it will be 4. We have 2, 2, 0. Again, you can cancel it out and you have 55. So you have 55 here. So the minimum value will be m into n, and it will be equal to 78 into 55. And what is this number? Go to the rough and do. You have 78 into 55, you have 0, 390. So you have 4,000. Is it right? Yes. So you have 4,290 tiles are required to pave this room. So this is the minimum number of tiles that will be required to pave the room. This is how you solve the question. So even though we did not have to, it was not stated that we have to find the maximum number of tiles, we still ended up finding the HCF and then using it to find the minimum number of tiles. So now let's move to the next question. Okay, so this question says that you have to find the greatest number of 6 digits exactly divisible by 24, 15 and 3 and 36. So the greatest number of 6 digit is, we know that the greatest number of 6 digit would be what? 3, 4, 5, 6. This. Is this divisible by 24, 15 and 36? No, it is not. Some number minus, if we subtract some number from it, then we will get a number that's divisible by 24. So if a number is divisible by 24, it will be a multiple of 24. So it will be 24 into some integer. And this is the greatest number that we are looking at. The greatest number that we are looking at is 999,999 minus k. Let that number be capital N. So N is this, right? We don't know what this k is. If we get k, then we'll be able to get the number N. Also, N equal to 36c and N is also equal to 15b. A, B, C are any integers. So N is exactly divisible by 15, so it will be 15b. N is exactly divisible by 36, so it will be 36c. N is exactly divisible by 24, it's 24 into some numbers, 24a. What we see from here is all these are equal to an. So 24a equal to 36c equal to 15b is equal to n is what we get from these three equations, right? What we did here is we are saying that the greatest number of 6 digits that is exactly divisible by these three numbers is n. Now the greatest 6-digit number is 99999, but this is not the number. there is a number that is subtracted from it to get the number which is divisible by all these three. So you have n equal to 24a, 36c and 15b because it will be divisible by all these three, which makes us say that 24 into a is equal to 36 into c is equal to 15 into b is equal to n. And from here, from this equation, we can say that n is a common multiple. N is a common multiple of what? 24, 36 and 15. Now what is the least common multiple of all these three numbers? There will be several multiples, right? There will be several common multiples for these three numbers, out of which the minimum is what? Minimum is the least common multiple or the LCM. So let's see what the LCM is. For that, you prime factorize it, and what you get here is you get 2 cube into 3 for 24. For 15 you get 3 into 5, and for 36 you have 2 square into 3 square. If you prime factorize, this is what you will be getting. And what is LCM? LCM is the highest power of all the primes. Product of highest power of all primes. Now LCM is what? LCM is equal to 2 highest power is 3. Then for 3 the highest power is 2, and for 5 the highest power is 1. So you have what? 8 into 9 into 5, which gives you 360. So the LCM is 360. N is what? A common multiple. That means if it is a common multiple of all these three, that means it will have to be a multiple of 360, because 360 is the first multiple of these three numbers. N is not the first multiple, it is nth multiple. So it is essentially 360 into n, where n can be some positive integer. So 360 is the least common multiple of these three numbers, and capital N, which is one of the common multiples, can be expressed in the form 360 into n. So now we have, from this given equation, 999 minus k equal to n, which is 360. In each of these you can get the same thing, because we are using this part where n is equal to 999999 minus k. So this is what it is going to be. Or 999 will be equal to 360n plus k. Now does it look familiar? Yes, it does. Here you have dividend equal to divisor into quotient plus remainder. If we get k, we will get n. So our purpose is to find k, and k is the remainder. Remainder of what? When 999 is divided by 360. So that makes our job a bit easier. So what we do is we simply divide. So you get 720 here, 2 times 972. Get a 9 here. So how much is it going to be? Is it 8? What is 360 into 8? It will be 7 times. So you have 0, 2, 25, 20. You have 9, 7, 2. Again you get a 9. You get a 2520. Again you get a 2799. Again you get a 2520. And finally, in the last step also, the remainder turns out to be 279. The remainder is 279. Hence the value of k is 279. Therefore n will be equal to 999 minus 279. So whatever that number is. So the greatest 6-digit number, which is exactly divisible by 24, 15 and 36, is going to be 999,720. Let's see it once more and understand it. Again, as I said, here we have to find the greatest number of 6 digits, but we have ended up finding the LCM. So the keyword greatest maximum is not same as finding the HCF, and when the question says that you have to find the minimum number or the least number, it does not guarantee, it does not necessarily mean that you have to find the LCM. So in this question what we did is, we are saying that the greatest number of 6 digits which is exactly divisible by these three numbers is capital N. Okay, so that greatest number of 6 digits would be what? It is not 999, which is actually the greatest 6 digit number, but that number is not divisible by all these three. A number lesser than this would be, so that number is 999 minus k, and that is equal to N. Now this number that we get is divisible by 24. So it will be 24 times 24 into a, where a is any integer. So n equal to 24a. Similarly, we say that n is equal to 15b and n is equal to 36c. From these equations we see that 24a will be equal to 15b will be equal to 36c, and it will be equal to the number n that we have set out to find. Which means you see that 24a into is equal to 36c is equal to 15b is equal to n would mean that n is a common multiple of this, this and this. So what we have written here is n is a common multiple of 24, 36 and 15. What besides n is a common multiple? The LCM is the first common multiple of all these three numbers, right? So we find the LCM of these three numbers by the prime factorization method. So 2 cube into 3 is what? 24. 3 into 5 is 15. And 2 square, 3 square is 36. The LCM is found out in which way? You take the product of highest power of all primes. So the primes are 2, 3 and 5. So for 2 the highest power in all these three is 3. So we took 2 cube. For 3 the highest power is square, so we take 3 square. And for 5 it exists just here and the highest power is 1, so you have 5 here. Multiply these and you get the LCM as 360. So 360 is the first or the least multiple of these three, least common multiple of these three. So n will be 360 into n, where n is any integer. So n has to be a multiple of these three, which means it has to be a multiple of 360 as well, because 360 is the least common multiple. So n is equal to 360n is what we got. Now from this we have n equal to 999 minus k. So instead of this n we can write 360n. This is what we have done here. Now we take the k to the other side, so the equation becomes 999 is equal to 360n plus k. And this reminds us of what? It reminds us of the Euclid's division lemma, which is dividend is equal to divisor into quotient plus remainder. We have to find the capital N, which can be obtained if we get the value of k. And k here is simply the remainder. Remainder when 999, which is the dividend, is divided by 360, which is the divisor. So we divide it and we get the remainder as 279, which means k is 279. If k is 279, then the value of n, which is what we have to find, will be 999 minus 279, which we found here, and it turns out to be 99720. So the answer is 99720. This is the highest 6-digit number that is exactly divisible by 24, 15 and 36. So just revisit this particular video in case you want to understand it further, and if you don't get it, then probably we will take it up again in the doubt class. Moving to the next question. It says there are 3 bells that ring at intervals of 4, 7 and 14 minutes. All the 3 ring at 6 a.m. When will they ring together again? So here we have 3 bells that ring. So you have bell A, you have bell B and you have bell C. So the bell, all of them at 6 a.m. they ring. So let the circle denote that they are ringing. This would ring again after 4 minutes. This would ring after 7 minutes. And this would ring after 14 minutes. So this is how they will keep on ringing. So you have something like this. They will ring at different times. Ultimately, after some time, they all will ring together again. When they will coincide, the ringing times will coincide. So we have to find this time when it will ring together again. So 6 a.m. is when the first ring together, and then the second time that they ring together is what we have to find. Okay. So let the bell A ring A times when they all simultaneously ring. B B times and C times. So the first bell rang A times before this time. Okay. So this is the time that we have to find. So from 6 a.m. to X a.m. or p.m. whatever it is, the bell A rung A times, the bell B rung B times, and the bell C rung C times. So you have between 6 a.m. and X o'clock, let this time be N, or let the time interval, instead of taking the time what exactly it is, let's take the interval. So this is the time that passed, right? From 6 a.m. to this particular time, the time passed be X. Okay. So X is what? X is equal to 4 times A. After every 4 minutes it rings, and it rings A times. So how much time passed? 4 into A. For example, if it rung just 3 times, how much time would it be? It will be 4 plus 4, 8 times, right? 4 into 2. 8 times it will ring thrice if you count the first one. So you have X equal to 4A. Similarly, X will be equal to 7B, and X will be equal to 14C, right? So these are the three equations that we have. From the three equations we get 4a is equal to 7b is equal to 14c. We have to find a, right? X, which is the time when they will ring together. So x is equal to 4a, 7b and 14c. So x is a common multiple of 4, 7 and 14. Now X, there will be many times when these three will ring together after this also, right? After X time again they will ring together. But what we have to find? The next time that they ring together. So we have to find the first X, first time that they ring together, which is going to be the least, right? If you go further on, you will not get the least time after which they'll ring together. We have to find the next time they are ringing together. So it's just the least one. So x is a common multiple and it has to be the least of the common multiples. This is going to be the first multiple. After x minutes again, there will be another multiple. After x minutes again, there will be another multiple. But are we interested in these times? No. We are interested in knowing the first time that they will ring together again, which gives you the least value of x. So you have x as a common multiple of these and it has to be least. So x has to be the least common multiple of 4, 7 and 14. So 4 is 2 square, 7 is 7 and 14 is 2 into 7. So the LCM is the product of highest powers of all primes. So the primes are 2 and 7. Highest power of 2 here is 2 square and the highest power of 7 is 1. So you have 4 into 7 is equal to 28 minutes. So after 28 minutes, the three bells are going to ring together again. And this is going to be the first time that they are going to ring together again after 6 a.m. Again after 56 minutes they will ring together. Again after 24 more minutes they will ring together. But the first time that they will ring together after 6 a.m. is going to be the least common multiple of these three numbers 4, 7 and 14, and it is going to be 28 minutes. Let's look at this problem once again to understand and grasp it better. Let me change the color of the ink as well, if I may. Okay. So you have there are three bells. So you have bell A, bell B and bell C. They all ring together at 6 a.m. So at 6 a.m. these three bells ring together. After that, the first bell will keep ringing after every 4 minutes. The second bell will keep ringing after 7 minutes. and the third bell will keep ringing after 14 minutes. So they'll ring at different points in time. Ultimately, after some time, they will again ring together. There will be some time after which they'll ring together. Again, there'll be further down the time, they'll again ring together. What we are going to find is when will they ring together after 6 a.m. The first time that they will ring together after 6 a.m. So we have to find this instance, which is the first time after 6 a.m. that these three bells are going to ring together. Now, what is it going to be? The first bell is going to ring after 4 minutes each. If it rung 8 times during this time, the total time from 6 a.m. to this time would be 4 into 8. After every 4 minutes, it rings. So this would mean that 4 into A is going to be equal to X, which is the time elapsed before the three bells ring together again after 6 a.m. So X is equal to 4A is the first equation. X equal to 7A comes from here. So X is equal to 7B because the second bell would ring b times, and x would also be equal to 14c. So you have x equal to 4a, 7b, and 14c, and we see from these three equations that x is a multiple of 4, 7, and 14. 4 is a factor of x, 7 is a factor of x, 14 is a factor of x, but x is a multiple of 4, 7 and 14. I keep on telling you about the factor and a multiple. There is a difference between what a factor is and what a multiple is. You've got to understand it clearly. X is a multiple of 4, but 4 is a factor of x. X is a multiple of 7, but 7 is a factor of x. And similar is the case with 14. And what we see is x is the common multiple of 4, 7 and 14. Now x that we have to find out is the least value because x will keep repeating. After every x minutes they are going to ring together again. But we are interested in the least value of x since we have to find the next time that they ring together after 6 a.m. So we are looking at the least value of x. So we have x as the least, x as the common multiple. So what exactly will x be? It will be the least common multiple of 4, 7 and 14, which gives us that x is equal to the LCM. So LCM of 4, 7 and 14 we calculate and we get it as 28. So after 28 minutes, these three bells are going to ring together again for the first time. So the answer is 28 minutes. This is solved using LCM. Now the next topic that we are going to take up is critical. It's linear, expressing the HCF as the linear combination of two numbers. Here it says that D is the HCF of 56 and 72. D is the HCF of 56 and 72, and we have to find x and y such that D equal to 56x plus 72y. X and y are also integers. Integers would also mean positive or negative, but not fractions. So when we are expressing as the linear combination, both x and y that we write here, they have to be integers. It could be positive, it could be negative as well. So d is equal to 56x plus 72y. And what will it be? So there is a step-by-step procedure or an algorithm that you can use to solve this problem. But the first step is calculating the HCF. D is the HCF of these two, so D can be easily found out by Euclid's division algorithm. And what is it going to be? 72 equal to 56 into 1 plus 16. The remainder is not 0, so you have the next step, which is 56 equal to 16 into 3 plus 8, and the next step we have 16 is equal to 8 into 2 plus 0. So the HCF is 8. So you have D equal to 8. And you have to express 8 as 56x plus 72y. And we have to find out what x and y are going to be. So listen carefully and watch carefully how we solve this problem. What do? We first step is to find the HCF. You just go on solving and you find the HCF using the Euclid's division algorithm method. Now from here Last but one step, you write the remainder as a combination of the other. So it will be 56 minus 16 into, you keep the remainder on one side and take the rest of the stuff on the other. So you have 8 is equal to 56 minus 16 into 3. And here also you do the same thing. So you have 16 equal to 72 minus 56 into 1. Okay. Now we have to write 8 as 56x plus 72y. So we have here 8 equal to 56 minus 16 into 3. So some part of our question is already done. So 56 is 56 into 1. So 8 is equal to 56x. We have already figured that it could be 56 into 1. It is not 56 into 1. It could be, because we have not sorted the other part. In the other part we have 16 into 3. Do we need a 16 here? No, we need a 72. So we need to get rid of 16. How do we do that? From the previous step, we see that 16 can be expressed in the form of linear combination of 72 and 56. So instead of 16, we write 72 minus 56 into 1 is 1. So you have this and multiplied by 3. 3 remains there as it is. So what does this become? It becomes 56 into 1 minus 72 into 3 plus 56 into 3. This 56 into 1 and 56 into 3 would combine together. What do you have? 56 is common. You have 1 plus 3 minus 72 into 3. So you have 56 into 4 minus 72 into 3. This is what we needed to have, 56 and 72. But here there is a plus. What we get here is a minus. So we can manipulate it a bit more. We write a plus here. And instead of 3, can we write minus 3? Minus 3 and plus outside, so it will ultimately give you the same result. So we keep a plus to just to make sure, just to compare, we write the plus here. And instead of 3, we write minus 3. This minus could be associated with 72 as well, but here we don't need a minus 72. So I don't associate the negative sign with 72, but with 3. Now you compare these two together. If you compare these two together, you will get x equal to 4 and y equal to minus 3. So we have found x and y. X is 4 and y is equal to minus 3, such that 8 is equal to 56x plus 72y. So this is how you solve this question related to the linear expressing HCF as the linear combination of two numbers. What do we do here? In the first step, we find out the HCF using Euclid's division algorithm method, step by step. The second step is, from the last but one step, you start writing a remainder as, or you take the remainder to one side and take the rest of the stuff to the other side, and you write it as a linear combination of them. So you have 8 is equal to 56 minus 16 into 3 here. And you have 16 is equal to 72 minus 56 into 1 over here. Now we have found that the HCF was 8. So D is equal to 8 and we have to express it as 56x plus 72y. So here we have an 8. We take 8, we write 56 minus 1 minus 16 is something that we don't need in this. So we have to get rid of the 16. How do we get rid? From the previous step, we find that 16 is 72 minus 56 into 1, which is 56. So instead of 16, I write 72 minus 56 and 3 remains as it is. Now we have 56 into 1 minus 72 into 3 plus 56 into 3, because minus and minus will make plus. These two would combine together to give you 56 into 4. 56 plus 56 into 3 is what? 56 into 4. I have simplified it and written here. So it's 56 into 4 minus 72 into 3. It is quite close to what we need, except this plus sign here, which has been replaced with a minus over here. How do we get rid of this minus sign? We write a plus and take this minus and club it with 3. We don't club it with 72 because in the final result we need a plus 72. So I don't bother too much and I put this minus with 3. So ultimately what I get is 56 into 4 plus minus 3 into 72 is 8. Now these two can be compared together, and by comparison we see that in place of x we have 4 and in place of y we have minus 3. So the answer ultimately that we get is x equal to 4 and y is equal to minus 3. And this particular question is an example of expressing, as I said, expressing HCF as the linear combination of two. This is what it is. There will be more questions in the assignment for you to do. In case you're not able to do it, again, we'll be discussing the same in the doubt class then. Okay, so the next subtopic is about the irrationality of numbers. But before getting into the irrationality of the numbers, let's recap the concept of real numbers, what rational and irrational numbers are, and then proceed to the next segment. So first question is, what is a real number? If there is something called a real number, is there something that's not real? Then the answer to it that is yes. Besides the real numbers, we also have in the number system we have imaginary numbers. So what is the differentiation between these two? Real number is any number a. If you talk about the definition of this, any number a is real if its square is greater than equal to 0. For example, if I give you three numbers, root 2, minus root 2, and root over minus 2, and I ask you which one of them is real and which one of them is not, then to find out the real number, you take its square. So you take the number root 2, its square is 2, which is greater than equal to 0. Hence, this is a real number. Similar is the case with this. If you take the square of this, you still get 2. So this number is also a real number. But what happens when you take the square of this number? When there is a negative sign under the square root, you get minus 2. Right? Because whenever you take the square, you just have to remove the square root. So if you take out the square root, what is left? Minus 2. So this does not fall in this definition, and hence this is not real. This number is called imaginary number. So any number whose square is less than 0 is an imaginary number, and any number whose square is greater than equal to 0 is called a real number. So this is the first definition that we need to be clear about. There will be a few questions that you'll be solving in the chapter on polynomials or quadratic where you'll be making use of this. These numbers are the imaginary numbers. You'll be taking it up in class 11th if you're taking mathematics. So imaginary numbers will be dealt with in that chapter. That's called the complex number chapter. But here we will confine ourselves to real numbers, and we know the definition now that any number a is called real if its square is greater than equal to 0. Now, any real number is segregated into two parts, the rational numbers and the irrational numbers. So a set of all real numbers has to be rational or it has to be irrational. So there is no other option. Now, within the rational numbers and irrational numbers, there are many ways in which you can differentiate between the two. The first is by definition, which says that any number which can be expressed in the form p by q, where p and q are both integers and q not equal to 0 is a rational number. This is the definition of a rational number. Any number which can be expressed in the form p by q such that both p and q belong to integer, z is called integer, and epsilon, or this symbol is called epsilon, it's not an e, the symbol epsilon. So it means belongs to. So p and q both belong to a set of integers, and q, that is the denominator, is not equal to 0 is a rational number. There is no definition for irrational number. So any number that is not rational is an irrational number. That's what irrational number is. You don't have any separate definition for an irrational number. If you cannot call a number rational and it is real, then it has to be irrational. The second is there are special numbers. There are special numbers which are irrational. For example, there is a symbol called e that you'll be using in higher classes, which is related to log. So this is, its value is close to 2.7, not exactly, it's close to 2.7. Another popular number that you know about is pi, whose value is approximately equal to 3.14159. It is not the exact value. Or 22 by 7. 22 by 7 is also not the exact value of pi. Coming and talking about pi, what exactly is pi? Is that a number? What exactly is pi? Lots of people don't know what pi is. Pi is actually a ratio. It is not a number, but it is a ratio of the circumference of a circle and its diameter. So pi, if somebody asks you what is pi, it is circumference divided by the diameter of the same circle. Okay? So this value of the ratio of circumference by diameter has not been calculated to its exact value. It keeps on going, but it is close to 3.14159, and it is also somewhat close to 22 by 7. So 22 by 7 is actually an approximate value of pi that we use in solving questions. It is not the exact value. Okay, so pi is a ratio of the circumference of a circle to its diameter. This is what you must know. And a rational number, so all whole numbers, all natural numbers, all these would fall under rational numbers. So if you have an integer, you can say straight away that it is a rational number. When you see pi, you can straight away say that it is an irrational number. So this is the second way of differentiating between them. The third way of differentiating between them is any number of the form root n, where n is a perfect square. An integer which is a perfect square is a rational number. What is a perfect square? 1, 4, 9, 16, 25. All these are perfect squares. So square root of any of these would be a rational number. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. Square root of 25 is 5. All these are perfect squares, and their square root is going to be rational number. And any number of the form root n, where n is not a perfect square, is what? An irrational number. For example, root 2, root 3, root 5, root 6, root 7, root 8, any number which is not a perfect square, its square root is going to be an irrational number. So this is again a differentiating factor. So if you see root 18, you can straight away say that it is going to be irrational number. The fourth is on the basis of decimal. Numbers can be expressed as fraction, as integers, as whole numbers. They can also be, but every real number has a decimal representation. So any terminating or non-terminating recurring decimal falls under rational number, and any non-terminating non-recurring decimal will be called an irrational number. How exactly is it? We'll be discussing it further, but just to have a snapshot of what is the difference between a rational number and irrational number, these are basically the four ways that you can differentiate between a rational number and irrational number. So again, coming back, a rational number by definition you can differentiate it from the irrational number by saying that any number which is of the form p by q, where p and q are both integers and q is not equal to 0, is a rational number. And if it is not a rational number, then it is an irrational number. Second way to differentiate is any integer, any whole number, any natural number is a rational number. and some special numbers like e, whose value is approximately equal to 2.71, or pi, whose approximate value is equal to 3.14159, is an irrational number. The third way to differentiate is if the number is given in the form of square root. So if it is of the form square root of n, where n is a perfect square like 1, 4, 9, 16, 25, 36, 121. All of these would be rational numbers. If the number within the square root is not a perfect square but an integer, it is an irrational number. So root 2, root 3, root 5, root 6, root 7, root 10, all these would fall under irrational numbers. And the fourth way is for if the number is given in its decimal representation, then a terminating or non-terminating recurring decimal will always be rational, whereas a non-terminating non-recurring decimal will be irrational. So these are principally the four ways that you can differentiate between rational and irrational numbers. Now we are going to go deeper into it and understand the third point, wherein I said that root n is a root n is a rational number if n is a perfect square, and it is not if it is not a perfect square. How do you prove that? How do you put that statement? The first and the second are by definitions, right? The third one, root n is an irrational number if n is not a perfect square, is not by definition. It has to be proved. So we are going to, in the next slide, we are going to take up this question and try to prove this using a number. Let's see what that question is. It says that you have to prove that root 2 is irrational. How do you prove? Irrational number doesn't have any definition, as I said. So if you can prove that root 2 is not rational, would mean that it is irrational. Okay. So this particular thing can be proved by the method of contradiction. And what you do here is let us assume that root 2 is rational. We are going to use the method of contradiction. So we have assumed that root 2 is rational. If root 2 is rational, then root 2 can be expressed in the form root 2 is equal to p by q, where pq belong to integers and q not equal to 0, and pq are co-primes. Now this is something interesting that I have brought in. If you go back to the last slide, you see that here in the definition of rational numbers, I have nowhere written that p and q are co-primes. However, when I say here that root 2 is rational, I add this extra bit of information. Does that change the definition of rational number? Can you say that what I gave in the previous slide here is an incomplete definition of rational numbers? If not, what does this mean? See, any rational number, for example, you take 4 by 6, okay, and you take the number 2 by 3. Are these two numbers same? They are same. This is the representation of 4 by 6 in its lowest form. Are both of them rational? Yes, both of them are rational. But there is a difference between them. Here, you don't have a common factor between the numerator and denominator. In the standard form, you don't have a common factor between the numerator and denominator, whereas here you have a common factor. 2 is a common factor in both these. So although both of them are rational, which is the definition, since they have numerator and denominator as integers and the denominator is not equal to 0. So both of them qualify as rational numbers, but this is the standard representation, standard form, where the numerator and denominator do not share any common factor. And if two numbers do not share any common factors, then they are called co-prime. So 4 and 6 are not co-prime since they have 2 as a common factor. 2 and 3 are called co-primes because other than 1, they have no common factor. So when I added this p and q are co-primes, it just means that I cancelled out all the common factors of the representation. Okay, so when I write p by q, I cancelled out all the common factors to get this number root. Okay, So P and Q, the definition would still hold, except that this representation that I am writing here is the standard form representation of the rational number root 2. Okay, so definition is not wrong if you don't use this. When you use this, it implies that you are writing the standard form of the rational number 4 by 6, for example. Here we are writing the standard form of the number root 2. Standard form of representation of the rational number 4 by 6 is 2 by 3. So both of them are correct. Here we are writing it to prove in this question. It's important in aspect in proving that root 2 is irrational. That's why I have used it. So now root 2 is equal to P by Q, where P and Q are both integers, Q is not equal to 0, and P and Q are co-primes, which means P by Q is the standard representation of root 2 in its rational form. We give this number equation 1. Now you square on both sides. We are justified in squaring on both sides. So you have root 2 square will be 2, and here you get P square by Q square, or P square is equal to 2Q square, which means 2 is a factor of P square. P square will be divisible by 2, right? If 2 is a factor of P square, therefore P square will be divisible by 2. So from here we can say that P square is divisible by 2, which would mean that P is divisible by 2. When some number is divisible by 2, we can say it is 2 into m. If it is divisible by 2, that means 2 is a factor of P. So we can write 2 into m, where m is any integer. I don't know what that integer could be. It could be any integer. Okay, since it is divisible by 2, so we can write P is equal to 2m. Now you take this 2m and you substitute it here. Instead of P, you write 2m. So you write 2m. So you have 2m square is equal to 2q square from here. Okay. So you have 4m square is equal to 2q square. Cancel this out. You have 2. So you have q square is equal to 2m square now, which means that q square is divisible by 2, which means q is divisible by 2, which means q can be written as 2 into n. Since 2 is a factor, or 2 divides q, so q is equal to 2n. So where n is any? Where n belongs to an integer. We don't know what n is, but it will belong to an integer. This we call equation A, and this we call equation B. So what do you have from A and B? What do you have? We have P is equal to 2m, Q is equal to 2n. They have a common factor. They have a common factor 2, right? They both have a common factor 2. But in our assumption from 1, we know that P and Q are co-primes. PQ are co-primes, which means they have no common factor. No factor is common in amongst these two. But above here we got that there is a common factor, which means there is a contradiction. There is a contradiction. Contradiction would mean that our assumption is wrong. If we use some result to prove something and it turns out that it is wrong, that means there is a contradiction, which means that our assumption is wrong. There must be some mistake in the assumption that we took. And what was the assumption? That root 2 is rational. Therefore, what do we say now? Root 2 is rational. This is a very interesting way of proving something, and it's called the method of contradiction. Let's see it again once more and understand it, try to understand it, how we obtained it. When we are asked to prove that root 2 is irrational, we cannot prove it by definition because irrational number doesn't have any definition. Instead, a rational number has a definition. And we know that if a number is not rational, it will be irrational automatically, provided it is real. So here we have assumed that root 2 is rational. When we assume that root 2 is rational, therefore we are implying that root 2 can be represented in the form p by q, where p, q are both integers and q not equal to 0. And p, q are co-primes. When I add this p and q are co-primes, it means that the representation p by q is in its standard form, like we saw here. 4 by 6 and 2 by 3 are representations of the same number, but 2 by 3 doesn't have any common factor among the numerator and denominator, whereas 4 by 6 has 2 as a common factor. So although both these numbers are same, this is called the standard representation of the rational number 4 by 6. Similarly, root 2 will have many forms, out of which we have taken the standard form here. We can take any form, we have taken the standard form. That's why we have added this particular statement that p and q are coprimes. Any number will have its standard form. Any number will have its standard form, and we have taken that form. So now when we square this on both sides, root 2 square becomes 2 and p by q square becomes p square by q square. So now you take q square to the other side, so you have p square is equal to 2q square. Now this would mean that p square is divisible by 2 since 2 is a factor. So p square is divisible by 2, because if you divide p square by 2, you will get q square, which is an integer. So it is exactly divisible by 2. So p square is divisible by 2, which would mean that p is divisible by 2. This also needs to be proved, that p square, if p square is divisible by 2, then p is divisible by 2. Although we are using here directly, there is another result that we will be using to find out that when p square is divisible by 2, p will be divisible by 2. But here, for simplicity's sake, we are straight away using the result that if p square is divisible by 2, then p is also divisible by 2. And if p is divisible by 2, which means we can write p as 2m, where m is any integer. We call it equation A. Now the value of p from here, which is equal to 2m, is substituted in this equation that we had. So you have 2m square is equal to 2m whole square is equal to 2q square. You simplify it and you get q square is equal to 2m square, which again means that q square is divisible by 2, which means that q is divisible by 2. Therefore q can be represented as 2 into n, where n is an integer. Now this is equation B. From the equation C and B, we have p is equal to 2m and q is equal to 2n. Now we see that both p and q have a common factor 2. But from 1 we have said that p and q are coprimes. That means they don't have any common factor. So there is a contradiction, because here we have got that they have, here we assume that they have no common factor, but we got that they have a common factor 2. So there is a contradiction from our assumption and what we obtained after solving. Hence, our assumption has to be wrong, because we did not arrive at a correct result. So when our assumption is wrong, we see that we assume that root 2 is rational. So what is the other option if it is wrong? The other option is that it is irrational. So this is how you prove that root 2 is an irrational number. Now, as I said, so this is, if you got this, then maybe I'll get into the other thing where I said that if p square is divisible by 2, then p is also divisible by 2. This is what I wrote here. This also has a proof, and it cannot be, I mean, you can use it when you get a proof for this question, you can use it directly, but you must know how you arrived at that result. Okay, so conceptually you must know. I'll just show it to you how that happens. Let p, I'll change the color of the ink. So you have p is equal to, from fundamental theorem of arithmetic, you remember that any composite number p can be represented as product of prime factors. Okay, I don't know what this number p is, and I don't know how many prime factors it has, but it will have k number of prime factors. I have called these prime factors p1, p2, p3. So from fundamental theorem of arithmetic, any composite number p is a product of its prime factors. Okay, so this is clear. Now what is p square? P square will be the square of all these. P1 square into P2 square into P3 square into P4 square, pk square. I don't know what these factors are, so I have just given them any, assigned them any symbol. So p square is going to be this. P1, P2, P3, all of them are prime numbers, prime factors. Now when I say that p square is divisible by n, which means when p square is divided by n, it should cancel out. Only then will it be divisible. If it does not cancel out, that means there will be a remainder and hence p square will not be divisible by n. When I say that p square is divisible by n, therefore when we divide p1 square into p2 square into p3 square into pk square by n, it will cancel out. Now we also said that p1, p2, p3, all of these are prime factors. So when n gets cancelled by any of these, prime factors would mean that they have just 1 and the number itself as its factor, which means n gets cancelled by any of these, which means 1 out of p1, p2, p3, p4 has to be n. Why? Because p1 or p2 or p3 will have a factor 1 or the number itself. So for the number n to get cancelled out, it has to be one of these. Only then will it cancel out. N cannot be a factor of these because these are prime factors. N can either be 1 or it can be the number itself. So n will be one of p1, p2, p3, pk for it to cancel out and make p square divisible by n. So n is one of p1, p2, p3, pk. Now what is p by n? P by n will be p1 into p2 into p3 into pk divided by n. And what do we get in the last result? That n is one of these. So n will cancel with one of the factors. Hence, you get an exact value. You don't get any remainder. The denominator gets cancelled. So p by n also becomes divisible by n. So if p square, if a composite number p square is divisible by n, then p will also be divisible by n. This is how you prove it, and you use it while proving the result that root 2 is an irrational number. Okay, I hope you got this. Now, as we discussed in this slide, this is by definition, these are standard numbers. Just by visualization you can differentiate between rational and irrational number. For this we proved just now that any number of the form root n, in the question that we had, we proved that root 2 is not a root 2 is an irrational number and it is not a perfect square. So we proved this. Now the fourth, again we have to prove that any terminating or non-terminating recurring decimal will be a rational number and any non-terminating non-recurring decimal will be an irrational number. How do we do that? For that we need to understand what decimals are. Any real number has a decimal representation, and any decimal is of three forms. It can be terminating, non-terminating recurring, or non-terminating non-recurring. What is the difference between all these three? A number say 0.2, 0.3175162. These numbers have a decimal and they end after a finite number of values, right? They terminate. So these decimals are called terminating. What are non-terminating recurring? There are numbers that you have seen, 3333, it goes on. 0.6666, it goes on, like 2 by 3. When you divide and you write its decimal representation, you'll get 0.66666 and it will never end. So 2 by 3. So this is a non-terminating, it does not stop anywhere, and it's a recurring because the number repeats itself. There could be numbers like this as well, 3232. So these are called non-terminating recurring numbers. And what is a non-terminating non-recurring? There would be numbers like pi whose value never ends. You keep on dividing, you will never end. You'll never end. For example, if you take out the square root of 3, you will keep on getting digits. You will never cease to get a recurring form or a terminating form. So those numbers are called, those decimals are called non-terminating, non-recurring decimals. How do we know which of these is a rational number, which of these is an irrational number? Because all real numbers are either rational or irrational, and all real numbers have a decimal representation. So out of these three, we have to figure out which of these is going to be a rational number and which of these is going to be an irrational number. The definition of rational number was, it can be expressed in the form p by q, where q not equal to 0 and p and q are both integers. This is what we know. So point 2, for any terminating number, how do we get rid of the decimal? How do we get into the fraction? You move the decimal to the rightmost digit, and the number of places that you move, you divide, in the denominator you put as many zeros. So for this, point 2 you have 1 0. So point 2 is equal to 2 by 10. You can cancel out the common factors and write it as 1 by 5. So 1 by 5 is the standard representation of the rational number, point 2. 2 by 10 is another representation of the same number. 0.3175162. You write 1 and you see how many decimals you have to move to reach the rightmost point. You have to move 1, 2, 3, 4, 5, 6 and 7. So you put 1, 2, 3, 4, 5, 6 and 7 zeros. So you get 3175162 divided by this number will be the rational representation of it. So terminating decimals are straight away we can see that they are rational. With non-terminating, non-recurring, can you write it as a fraction? You cannot, because after 1 you have to reach to the rightmost part and you do not know where the rightmost part is. So you keep on adding zeros, but you never know when you have to stop it. So if you don't know what p is, if you don't know what q is, how can you represent it in the form p by q? So this number cannot be a non-terminating, non-recurring number, cannot be represented in the form of a rational number or p by q form, and hence it is clearly irrational. One look at the non-terminating recurring numbers and you would be tempted to say that this would also fall under irrational, because again you cannot move the decimal to its rightmost point. But the advantage or one beauty of a non-terminating recurring number is that uh, there is repetition in it. You know the repetition on it, so you can write the next digit. In a non-terminating, non-recurring number, you go on intuitively, you cannot write the digit after 9. Whereas in a recurring number, you know intuitively what the next digit would be. For example, in 0.3333, you would know that the next digit would be 3. In 3.3232, you would know that the next two digits would be 32. So there is something unique about these numbers. Can that uniqueness be used to figure out whether it is rational or irrational? Let's see. Let's take the number 0.66. So you have, let x is equal to 0.6666 and going on. You can also write it as 0.6 recurring. Recurring is by putting a bar or a dot. So here also you can write 0.33. Recurring can be written as 0.3 and a dot over it, or a dash. And this number can be written as 0.32 dash or 0.32, and over both of them you can put dot. Okay, so if there are more than one digits, you put a dash, and if there's just a single digit that's recurring, you put a dot. That's the standard notation. So you have x is equal to 0.6666, and we have to figure out whether it can be represented in the form p by q. Now I multiply this number by 10. If I multiply this number by 10, I have to move the decimal by one place. So 10 into x will be 6.6666. Okay. Now, if I subtract these two equations, if this equation is number 1, this equation is number 2, and I do 2 minus 1, what do you get? On the left hand side, 10x minus x will give you 9x. And what do you get here? You get, after the decimal point, you have only sixes. So all of these would vanish. And here you have 6 minus 0, you'll get 6. So what you get is 6.0000. And what is 6.0000? It's 6. So x becomes 6 by 9, which is 2 by 3. And what was x? X was 0.6666, and x can be written in the form p by q. Hence 0.666666, which is a non-terminating recurring number, is a rational number. There are other rational numbers also, other repeating numbers also, with which you can check, and always you can end up getting them as a rational number. We will take a couple of more questions. You have already done it in class 9, but we will see if we can take up more questions within the given time frame, and see how recurring numbers of different forms are also rational numbers. So in here we showed that terminating decimal is a rational number, non-terminating recurring number is a rational number, but a non-terminating non-recurring decimal is not an irrational number. It is an irrational number. So this is what was the fourth difference between rational and irrational number. This is how you do it. Now let's move further ahead. So here we have three questions, and they are all non-terminating recurring numbers. Here you see that after the decimal 2 is recurring, so you can write this as 1.2 recurring. This is 0.32. There is a block of two numbers that's repeating, and here you have, after the decimal, there is one digit 7 that does not recur, but beyond that the other two digits keep recurring. So this is how you write it. These are the three numbers, and we will check how these turn out to be rational numbers. So starting with the first question, we take, if we are taking the first one, so you have x equal to 1.222 and so on and so forth. Now, as I said, in such types of questions, what you need to do is you have to move the decimal to, you have to jump with the decimal to a place where the repeating, after the repeating block. So the repeating block here is 2. So you jump with the decimal by one digit, because the repeating block is just the digit 2. So to jump from here to here, you need to multiply x with 10, because as you keep on multiplying, the decimal moves to the right. If you keep on dividing, the decimal would move to the left. So when you multiply this equation with 10, what you get is 12.222 and so on. Why we did this? Because to make sure that you have a rational number, you have to convert it into fraction, and you have to get rid of the decimal. And the only way that you can get rid of the decimal here is if you have same digits after the decimal. So when you subtract, you get a 0 after decimal. So 0.000 would become, you can remove the decimal point if there is only 0 after the decimal. Here we subtract this equation from this. So you have, if this is equation 1 and this is equation 2, you do 2 minus 1, and this will imply on the left hand side you have 9x, and on the right hand side you have 11.000. And what is 11.000? It's 11, right? So you can write it simply as 11. Therefore you get x is equal to 11 by 9. And what was x? X was 1.2 recurring. So the rational representation of this decimal number is 11 by 9. Now let's take the second question. The second one is x equal to 0.3232 and so on. Now here again you have to take the decimal and jump by one repeating block, and the repeating block here is 32, because 32 is repeating. So you jump two numbers. When you jump by two digits, you have to multiply with 100, because you are jumping by two places. So this will give you 32.3232 and so on. Now again you subtract this from this. So on the left hand side, what do you get? On the left hand side you get a 99x, and on the right hand side, beyond the decimal point, you get 0, and the other side you get 32. So you can write x is equal to 32 by 99, which is a rational representation of the number 0.32 recurring. The third one is a bit interesting because it's not like the numbers that we have dealt with so far. How is it different? It's different because in the other numbers, after the decimal, the repetition started. So beyond this point, 222 was a repeating block. In here, you have 0.32 as the repeating block, but here 0.721 is not the repeating block. 7 is not a repeating number, only 2121 is. Now, if you go ahead and move this, if you jump here, the decimal would come here. So beyond decimal you will have 212121, but in the earlier number you have 0.7212121. So when you subtract, you will not get a 0 after decimal. To make it more clear, what I am saying is if you have x is equal to 1.72121, so on, if you move it by 3 places, that is if you multiply with 1000, what do you get? 1721.2121. So when you subtract these two numbers, after the decimal, the digits are not same. So you will not get a non-zero number, and hence you will not be able to write it as a number and represent it in a rational form. So this method is not going to work here. And the reason for that is this number is different from the other two that we have taken up so far. In the other two numbers, after the decimal, the repetition had started. But in here, the repetition did not start right after the decimal point. So what you do is, first you convert this number into a number which is similar to these. So how do you do that? If I jump by one place, multiply it with 10 and write it as 17.212121, does this number become similar to this? It does. Now your 10x is going to be the x that we were taking so far. So now what you do, the logic was simple. You move the decimal to the decimal after the first repeating block, which is 21. So you move 2 digits. So you multiply 10x, which is the new x that we are taking, with 100, and you get 1721.212121. And now you subtract these two equations. So you have 100 into 10 is 1000. So 1000x minus 10x would give you 990x. And on the right hand side, what do you have? You have 1721.2121. And above you have 17.2121. You are subtracting 10x, 1000x from 10x, 10x from 1000x, and not x. X is left out now. So when you subtract these two, beyond the decimal you get a 0, and here you get 4071. That's 1704. Here is the rough work that we are doing. So you get 1704. Therefore x will be 1704 by 990. You can reduce it to the standard form as well. I'll leave that task to you. So this again will be a rational representation in the form P by Q of the non-terminating recurring number. So in all the cases we see that a non-terminating recurring decimal always gives a rational form when it is converted, and hence it is a rational number. Let's move to the next topic now. It says, how do we identify if a given rational number is terminating or non-terminating recurring decimal? Now, non-terminating recurring is also called repeating. Please note this. So what it says here is a rational. We have seen here that an irrational number is a non-terminating, non-recurring number. But for rational number, there are two options. It could either be terminating, right, or it could be repeating, right. So just by looking at a rational number, can you find out whether it will be a terminating decimal or a repeating decimal? There is a way out to do this. And what is the way? It says that every rational number having terminating decimal expansion can be expressed in the form a by 2 to the power m into 5 to the power n, where a is an integer and m and n are non-negative integers, is a terminating decimal. So it's saying that any rational number which is of the form a by 2 to the power m into 5 to the power n is a terminating decimal. How is that possible? Let's have a look at that. For example, I say zero point 0.7. Zero point 0.7 is a terminating decimal. Why? You can move it and you can write it as 7 by 10. Similarly, 0.6172, it's a terminating decimal. Why? Because we can again divide it by 10 by 10,000 and get a rational representation. In both these numbers, what we see in common is that the denominator has a power of 10. If you prime factorize 10, what do you get? 2 into 5. If you prime factorize 10,000, you would be getting 2 to the power 4 into 5 to the power 4. So 2 and 5 will again be the prime factors in the denominator. So in whichever terminating decimal that you take, there will always be a power of 10, and hence its denominator will always have 2 and 5 as prime factors. Let's take another number. Let's take 3 by 8. Now, you would be tempted to say that since it does not have a 10, it will not be a terminating number. But let's see if we can make it. When we divide it, what do you get? You take 3 here, you get a 3. You find that it is a terminating decimal. Its decimal representation is 0.375. And this can be written in the power of 10. So 3 by 8 is a standard representation of the number 375 by 10 by 1000. So even though this number does not have a power of 10 in the denominator, one of its form does have it, right? So this turns out to be a terminating decimal. So again, this relation would hold true, or this observation would hold true, that any terminating decimal will have a power of 10 in the denominator, which means it will have 2 and 5 as its factors. Now, which means that this would hold true that in all these the numerator is a. So here you have 375, you have 6172, you have 7 here. So a is the numerator. In the denominator, what we see here is that the powers of 2 and 5 are same in all these. In 3 by 8, you can write it as 375 by 2 cube into 5 cube. We see that the powers of m and n, powers of 2 and 5 are same. But here they have written it differently. They have written m into n. We could have simply said that any number of the form 10 to the power n is a terminating decimal. But they have explicitly written it as a by 2 to the power m into 5 to the power n. So why the need to do that? Why use separate variables in the denominator? The answer again is in this particular question. What happens here is, here you have 3 by 2 cube. It still ended up being a terminating decimal. Why and how? What we did was we multiplied and divided it by 5 cube. It will not change the number. When we do that, on the numerator side we got 375 and denominator became 1000. Okay, so any number, even if it does not have a 5 or if it does not have a 2, can be converted into a number which is a power of 10, right? By multiplying and dividing it by the required number. So that is why the m and n can be different. This will be one of the forms of a decimal, of a terminating decimal, but some numbers will be in such a representation wherein the power of 10 is not seen. But we can always go ahead and convert it. We can always go ahead and convert it into a form such that it becomes a numerator divided by power of 10, which means it is a terminating decimal. So that is why you have different powers of m and n. For example, uh, another example that I would take is 2 by 5. Okay, now 2 by 5, again it does not have a 10 here, but it will have a 10 if we multiply and divide the numerator and denominator by 2, which will not affect the number because 2 cancels out and it still remains 2 by 5. Now what does the number become? It becomes 4 by 10. It has a 10 in the denominator, which makes it a terminating decimal. So the number given was 5. So here the power of 5 was 1 and the power of 2 was 0. Why? Any positive number to the power 0 is 1. So you could always replace, if there was no number given, for example in 3 to the power 8, which was 3 by 2 to the power 3, I could easily write it as 5 to the power 0 because it is same as 1. So it will not affect the number. So this number is of the form a by 2 to the power m into 5 to the power n. So a is 3, m is 3 and n is 0. So such numbers, this is the generic form. So generic means it will hold true for all terminating decimals. This will hold true for only certain terminating decimals in their standard form. There would be a lot of terminating decimals such as these which will not be written in this form, but they are still terminating. So this is the general form of a rational number which is a terminating decimal. This is a specific form, okay, standard notation form. So any number that you see in the form a by 2 to the power m into 5 to the power n will be a terminating decimal. Why? Because it can be converted into a form a by 10 to the power n, and if it can be converted into the form a by 10 to the power n, which means it will have 10 power of 10 in denominator, that means it will be a terminating decimal. So let's take a few examples and check out if the given rational number is a repeating decimal or a terminating decimal. Again, another important thing to note is that in the denominator you should not have any other prime factor other than 2 and 5, or 2 or 5 or both. Nothing other than 2 and 5. Now let's take this number, the first number. Is it of the form a by any number of the form? We know that any number of the form a by 2 to the power m into 5 to the power n would be a terminating decimal. So this in here you have a as 23, you have m as 3 and n as 2. So this becomes terminating decimal. Why? Because it can be written in the form a by 2 to the power m into 5 to the power n. What about the second number? We cannot. The denominator does not seem to be having a power of 2 and 5 only. So what we do is we first factorize and cancel out the common factors. The way to judge in these questions is first to write the factors, cancel out the common factors, and then judge. 77 is not a prime number, so you have to write it in its factors, and 210 is what? 3 into 7 into 2 into 5. This will be its factorization. Now here we see that the 7 would cancel out, right? And what you will be left with is 11 by 3 into 2 into 5. Does this qualify? No, because here the numerator is fine, but in denominator you have two powers of 2 and 5, but you also have a power of 3, which is not allowed, which means this is going to be a recurring decimal. It is not going to be terminating. This was a terminating one. This is not going to be a terminating decimal. What about this? Again, you have to first factorize. So you have 1715. You take out its factors. What do you get? 3, 4, 343. You have 7. So you have 7 cube into 5 by 2 cube into 7 cube. Remember that in such questions you have to cancel out the common factors, and for that you need to factorize. So 7 cube gets cancelled out and you have 5 by 2 to the power 3. Does this qualify? Yes, it does, because it can be written as 5 by 2 to the power 3 into 5 to the power 0, because 5 to the power 0 is 1, and here you could have written it as 2 cube into 1. It will not make a difference. So this is of the form a by 2 to the power m into 5 to the power n, and hence this becomes a terminating decimal. If you hadn't factorized it, you would have written it as a non-terminating recurring decimal, because other than the power of 2, there is a power of 7 which is not allowed in standard in this generic representation of a rational number which is a terminating decimal. Again, here what do you have? You have 3 into 5, 16. Okay, so 16 and 100. So you have 3 into 5 by 2 to the power 4 into 2 square into 5 square. What happens here? You don't need to worry about anything because denominator does not have anything other than 2 and 5. So this qualifies as a terminating decimal. 256 by 4050. 256 is what? 2 to the power 2 to the power 6 is 64 and 2 to the power 6 is 256. And what about 4050? 4050 is you take 5 here, you have 810, take another 5, you have 3 6 162, you have 81, so you have 3 to the power 4, you have 2 into 5 square into 3 to the power 4. 2 gets cancelled, you get 5 here, but denominator has a power of 3 which is not allowed, and hence this is not a terminating decimal. The other long way to solve this question would have been to actually divide and check whether it turns out to be a terminating decimal or a non-terminating one. But this is a very simple trick, and you just have to remember the standard representation, the general representation of a rational number which is a terminating decimal. M and N can be any positive integers or a 0. A is an integer. So any number that can be represented in this form will be a terminating decimal, and if it is not, it will always be a recurring decimal, because non-terminating non-recurring decimal can never be represented in the form of p by q, so that is out of question. Okay, so with this we come to the end of the chapter, and I would encourage you to take up the questions and post your doubts on the doubt section of our app, and the doubts will be taken sequentially, and if we and time permitting, we'll be taking up any other questions as well. So even if you have a problem with any concept or any problem related to the assignment or any other problem that you have encountered in your reference book in the school or wherever you have, you can just post it there and we'll be taking it up in the next doubt class that we have. Okay, so have a good day, and I hope you enjoy this lecture. Thank you.